Okay, so I'm going to look to do a series of videos just to look through some tricky questions for the SL analysis course at the request of some of my students. So let's just dive in. First one I'm looking at here. A couple of things spring to mind as I'm looking at this. First of all, chunky marks assigned to this, 14 marks, non-calculator. And as soon as I look at it, we're talking about a geometric sequence, and I'm looking straight away at this sequence, and I've got some logarithms within there. So a lot going on, and what my advice is really in order to get started on this is to not get too bogged down in the idea of this being a logarithm. Okay, a logarithm at its heart is just a number. Okay, it applies some rules, and it draws upon the rules of indices in order to then facilitate greater manipulation, but it is just a number, and we can just apply it in the same way as we would any number. So in that sense, what we need to do is we need to just dive in and get started. I'm looking first of all at this part A, and we need to find the common ratio. So for A, the common ratio R is going to be a term divided by the previous term. Now I don't really have any options here, I've only got two terms, so in this instance all I need to do is do this second term divided by this first term. So I'm just going to plug in those values here. So R in this case is equal to 2 log base 3 of x divided by 3 log base 3 of x. Now what's happened here, which is quite nice, is I've got just the number 2 multiplied by log base 3 of x, and the number 3, which is multiplied by that same thing, log base 3 of x. So I have a fraction with the same thing top and bottom, numerator and denominator, which means they can cancel out. It has no effect on the number, which means my R value, the common ratio that I've found, is equal to 2/3. So that's my answer. Oops, I can't write 2/3. 2/3, that's my answer for part A. Okay, part B then. Let's zoom in a little bit so that I don't take up all the space. For part B, let's just refer back to it. It's saying here to show that the sum of the infinite sequence is 9 log 3 of x. Always quite nice when you get a show that question, because then we can have confidence in our answer. So again, same process. We're not going to think too much about the fact that we're dealing with logarithms. We're going to reach for our formula booklet and look up the sum of the infinite geometric sequence, which is there, sum to infinity. That's what I'm going to copy out. So my s to infinity in this instance is equal to u1 over 1 minus r. So let's plug in all the things we know. My sum to infinity should equal the first term, u1. Now if I go back up to u1, that should be 3 log base 3 of x. 3 log base 3 of x divided by 1 minus my common ratio, which I just found out, 2/3. So my sum to infinity is equal to 3 log base 3 of x divided by a third. Now, dividing by a third is the same thing as the same process of as multiplying by 3. So I've got that numerator which I can multiply by 3, which means my sum to infinity should equal 9 log base 3 of x. And you know what I'm going to do? I'm going to now check what we've got. 9 log base 3 of x is what we were hoping to arrive at. So I'm confident that that's correct. I'm also confident, because I used it in order to arrive there, that my answer to part A is correct. So it's a good exam kind of technique there to be able to check. Okay, kind of a little pause in the question now. We've got a new paragraph starting here, and there's something new going on. So the first 3 terms now of an arithmetic sequence, so we need to switch our focus when it comes to the formulae that we're using. Is this log base 3 of x, log base 3 of x over 3. Okay, so we've got 3 terms there, and we're asked to find first of all the common difference d. Now if you recall, common difference d is any term subtract the previous term. Now I would just always choose the second term minus the first. You could choose the third minus the second, you should get exactly the same answer, just personal preference I suppose. So for part C here, I'm going to say that my common difference d will equal the second term, which in this case is log base 3 of x over 3 minus log base 3 of x. Okay, now the fact that we've got logarithms is going to come into play, and it's going to come into play because we can manipulate this in a special way because it's a logarithm. So hopefully we know in terms of our laws of logarithms, in fact if we look at them here, what have we got going on? This is in our formula booklet, believe it or not. We've got a subtraction, so we can write it as a single logarithm. So in this instance, that's going to be equal to log base 3 of x over 3, and it's going to be divided by, I really dislike having layers and layers of fractions. So instead of writing this as a fraction, I'm going to write this as being x over 3 divided by x, which hopefully shows that what we're actually doing here enables us to cancel these two. We've got an x and we're dividing by an x, which leaves the third. So what we're left with is equal to log base 3 of a third. Now it does say in the question that we needed to leave our answer as an integer here. So we need to think about undoing this logarithm. Now you will be able to convert them in many different ways. The numbers as you read it should be the base, the answer, and then the power. So as you're undoing it, we've got log 3 to the something is equal to a third, and that's what we need to work out. So in order to undo this one, I might then say therefore 3 to the power of something is equal to a third, which is going to be -1, right? We know from our laws of indices. So in fact that should have been a d, shouldn't it? So let's change that for a d. So therefore, which implies that d is equal to 1, so -1. From our laws of indices, we know that should be -1. So it's just undoing that. Hopefully that makes sense. I think I might have said the wrong thing in the middle there, but I think I recovered it in the end. Okay, we're not done yet. We've got parts D and E, and I've run out of space. I might go back this way. Oh, that's quite nice because it's given me the same question. Didn't think it was going to do that. So I need to do part D. It's quite handy because I can still refer to it. So D, show that sum of the 6 terms is equal to 6 log base 3 of x minus 15. Okay, so now we're looking at the sum of an arithmetic sequence. So that is this formula here. And because we don't know the 6th term, we're going to have to be using this one. So that is S6. I'm going to replace my n's with 6's. Is 6 over 2. 2u1. 2 times, now u1 is this one in my arithmetic, log base 3 of x. And 2u1 plus n minus 1, do you know what, I can do that in my head. 6 minus 1 is 5, times my common difference d, I just worked that out, d here is -1. So I'm going to plug that in. So times by -1. And that's my formula. So let's tidy this up a bit. The sum of the 6 terms is equal to 3 times 2 log base 3 of x minus 5. And if I expand it, my sum of my 6 is equal to 2 times 3 is 6 log base 3 of x. 3 times -5 minus 15. I'm hoping that's the final answer. 6 log base 3 of x minus 15. Wonderful. Okay, part E then. Given that sum of the 6 is equal to 1/3 of the sum of the infinite geometric sequence, find x given your answer in the form a to p, where a, p are integers. Okay. I'm not going to have enough space for this, am I? Tell you what, can I move this out of the way a little bit? I can certainly move it. I was hoping to make it a bit smaller as well. Oh yeah, resize. All of a sudden, I've got space. Okay, here we are then. E. What do we have? I have sum of the 6. Well, that was given to us. So even if you didn't manage to arrive at this, we can still approach this question. So sum of the 6. So we're saying 6 log base 3 of x minus 15 is equal to 1/3 of the sum of the infinite geometric sequence, is equal to 1/3 of the sum of the infinite geometric sequence times 9 log base 3 of x. And we're going to start doing some algebraic manipulation. First thing I'm going to do is multiply 1/3 by 9. That looks like something that I can do quite easily. So I've got 6 log base 3 of x minus 15 equals 1/3 of 9 is 3 log base 3 of x. Now if I move my logarithms to one side and my numbers to the other, by subtracting and adding, I've got 6 log base 3 of x minus 3 log base 3 of x is equal to 15. Now, I'm going to have to use one of my laws of logarithms now. I can't apply this idea, this subtraction idea that I had previously, whilst I've got this coefficient of the logarithm. Coefficient, yeah, good word. So what I'm going to have to do is I'm going to have to use my law of log, this one here, in order to move things from this position up to the top, which should be something that we're familiar with. This 6 is going to become x to the 6, this 3 is going to become an x to the 3. So again, what have we got? Log base 3 of x to the power of 6 minus log base 3 of x to the power of 3. That equals 15. And now I'm going to use my other law to combine my logarithms. So I can say log base 3 of x to the 6 over x to the 3 is equal to 15. Now the 6 and the 3 will cancel. I can subtract them using my laws of indices. So this subtract this, I can write a single x within there. I've run out of space again, haven't I? I'm not going to compromise my workings. So what I'll do is I'll move me up a little bit. I'll see if I can just resize again. Get this a little bit smaller. It's over here. Let's go in a bit, and I can say then I've got log base 3 of x cubed is equal to 15. Now I'm using that base answer power idea that I referred to in the previous part of the question, and so what I can say is that then no, I need to move it down in order to undo it, don't I? Okay, so now I'm going to undo kind of what I did previously. There's one way of thinking about it. So this is going to be 3 log base 3 of x is equal to 15. I can divide both sides by 3. So log base 3 of x equals 5. So then now I'm going to use the base answer power as a normal exponent, base answer power. So x equals 3 to the 5. Which I think if we come out, this is exactly the form that we were hoping for, something to the power of something else. So I'm fairly confident that that's the correct answer. And that's how I would approach that one.